Good morning, students. A very good morning to you. Good morning, S. Verma. Good morning, Tarun. Lucifer ji, good morning. Gyanvi Sharma, a very good morning. Yes, students, I hope you are all well. And yes, I'm back with full energy and vigor. So, Asmit back, good morning. Jatin Raj, good morning. Solar DS, yes, good morning. Satvik Reddy, good morning. So students, here at Careers 360 Mega Revision Marathon, you are doing with me JEE Main, JEE Main, June 2020, okay, revision. Dalip, good morning. Yeah, I'm fine, Asmita, thank you. I'm now fine, I'm now all okay. Thanks for asking. Yeah. Yes, Solar DX, good morning. So, here at Career 360, we realize that what loss you are presently facing when there is a lockdown period. So, here we have come up with an online mega revision marathon, right? So, here we are going to assist you with some lessons, practice sessions that would help you in your preparation for JEE Main. So, all the best students. Yes, let's begin. So today our topic is matrices and determinants. This is a very important topic, students, and those of you who aspire to become computer engineers, it becomes the mainstay for computer engineers. Maths contains, okay, Sanskriti, a very good morning. So matrices and determinants both will take, the theoretical portion we'll take today. Okay, Ankita Yadav, good morning. So matrices. What is a matrix? Matrix is a set of m by n numbers, real or complex. Okay? Do understand that the numbers can be complex as well, Hannah? Or objects or symbols arranged in a form of a rectangular array. Meenakshi Sundaram, good morning. Good morning, Tanya. So, having m rows, so whenever we have m by n, m goes for rows and n stands for columns, and bounded by bracket is called a matrix of order m by n. That's how we call it, order m by n. Read it as m by n matrix. Okay, good morning, Venkat. So let's go to the next slide. I hope I have defined a matrix m by n. So types of matrices. What are the type of matrices? There are many of them. First of all is a row matrix. A row matrix, a single row is there. Hannah? A column matrix. Ashmit, good morning. A column matrix is one which has a single column. Okay? No confusion in that. Then equal matrices. What are equal matrices? Equal matrices are one which are exactly identical. They will have the same order, as well as each element corresponding to the position, they would be same. Aij is equal to Bij. Here I represent the position of the ith row and j represents the position of the jth column. Okay? Square matrix. A square matrix is a matrix whose number of rows is equal to number of columns. We know that only then a determinant is defined whenever we have a square matrix. Then we have null matrix. Null matrix when each of the elements is 0. A diagonal matrix. Yeah, here some kind of confusions exist for the students. There is a diagonal matrix, there is a scalar matrix and all that. So first of all, let's consider the diagonal matrix. A square matrix, first of all, it's a square matrix. It's called as a diagonal matrix if its all elements except the diagonal elements are 0. So diagonal elements need not be equal. The diagonal matrix has all the elements 0 except the diagonal elements. Okay. Then we come to the next slide. So we have an upper triangular matrix. By the way, we have a scalar matrix as well. A scalar matrix is one in which is a diagonal matrix, but all the diagonal elements are equal. Now, upper triangular matrix. What's an upper triangular matrix? Again, it's a square matrix. And what kind of a square matrix? Whose all elements below principal diagonal element, although it's called upper triangular matrix, that means all the triangle elements which are above the principal diagonal elements are not zero. So here these are zero. Below the triangle they are all zero. It's called an upper triangular matrix. Okay. So as you can see is in the example that this is the principal diagonal. Below it, below principal diagonal, they are all zero. Okay. Then we have a lower triangular matrix in which this is just the opposite of the upper triangular matrix. It is one in which the principal diagonal elements above are all zero. Here they have wrongly written upper triangular matrix. It is lower. Please do the correction. It is lower triangular matrix. So there can be certain questions in permutation combination and they can be made like this is lower. So let's do a question here. Let's say I have to make a 4 by 4 matrix. And let's say I have to make a lower triangular matrix. 4 by 4 lower triangular matrix I have to make. And I only have to use 1 and 2. These are the elements which I can make use of. Can you tell me how many different matrices I can make? Yes, tell me student. How many different matrices I can make? Yes. Can I expect an answer? So 4 by 4 matrix, I'll use the elements as 1 or 2. How many different matrices I'll make? Yes, students. Tarun, 4 only. Oh, 2 raised to power 16, Sanskriti Mishra. Solar RDX 16. Okay. So tell me first of all, in a 4 by 4 matrix, it would be this one. 4 by 4 matrix would be up to here. How many diagonal elements does it has? It has 4 diagonal elements. 4, 3, 2, 1. So that is 10. Hello students, listen. I'm in lower triangular matrix I am making. How many elements does it has? Except these zeros. So here I'll have to fill zeros only. Beta? Now here what are the number of elements? 4 plus 3 plus 2 plus 1. That would give me the total. Yes, that's it, Giridhar Sunil. 2 raised to power n. That is the right answer. So that would be 4 into 5. Sum of first 4 natural numbers. That would give me 10. Now, every element I can make use of 2 elements, 1 or 2. So this can be done in 2 ways. This can be done in 2 ways. This can be done in 2 ways. So I'll multiply. Dilip Ratha, very good. 2 raised to power 10 would be the total number of cases. Am I right, students? Yes, 2 power 10. Yes, Meenakshi Sundaram. Yes, Lucifer. You're right only. Okay. So we go to the next question. Next slide, I mean. 2 matrices can be added. So we are talking about addition of matrices. By the way, unit matrix you well understand. Unit matrix is a type of scalar matrix in which all the diagonal elements are 1. It's a square matrix in fact. And unit matrix is in fact can be compared as 1 with whatever you deal in arithmetics. Okay. Now addition of matrices, we all understand that addition of matrices is only valid when the order is same. When the order of the matrix is same. So subtraction of matrix, simply the order has to be same, then we can subtract it, and each of the respective elements would be subtracted by the elements of the other matrix which is present in the respective position. Then scalar multiplication. Now whenever we multiply a matrix with a scalar, then here you have to understand, because in determinant there is a slight difference and in matrix there is a slight difference. then the matrix obtained by multiplying every element, every element of A is multiplied by scalar K. So that is known as scalar multiplication of the matrix. Of course, you can multiply any scalar to any matrix. Okay, let's see multiplication of two matrices. This is important and I hope you guys are very comfortable in it, but still let me revise it. So two matrices AB are confirmable, that is they are valid for multiplication. When is the product AB is valid? When the number of columns in A and the numbers of rows in B are equal. This is how. Yeah, Ashmit, I am very fine. Thank you, Ashmit. Otherwise, these two matrices will be non-confirmable for matrix multiplication. Okay. So AB is defined when number of column of A is equal to number of row of B. Okay. BA is defined only if column of B is equal to number of columns of B is equal to Senthil, no problem. Join us. We are only at multiplication. So A is ij m cross n. So here we realize that to define AB, n and n, I mean the number of rows here and the number of columns here, the number of rows here should be equal. So it results into a matrix, you see, which is m by p. This results into this product. Okay. So this is about multiplication. Now, in multiplication of a matrix, I would like to know one thing. If A into B matrix is confirmable and AB is equal to a null matrix, then does it implies that A is 0 or B is 0? Yes, students. Either A is 0 or B is 0. Can we say that? So we have now multiple properties of multiplication. Obviously, it is not commutative. It may or may not be commutative. It would depend upon the respective. Yes, you're right, Scalar dx. That's A or B is not. That's written in the last sentence here. If AB is equal to a null matrix, it doesn't imply that A is 0 or B is 0. Okay. Then matrix multiplication is associative. So ABC is equal to AB into C. That's Preetham. Good morning. So matrix multiplication is distributive over addition. This all helps us. A into B plus C is AB plus AC. Okay, this I have already discussed. Now let's move on to the next part. Transpose of a matrix. So if we change the number of rows, if we change the rows to columns and columns to rows, we get a transpose of a matrix. That's how we define transpose of a matrix. So we change the rows to columns and columns to rows. Changing rows into columns or vice versa will give transpose of A. Transpose of A is denoted as A dash, A raised to power T or A raised to power capital T. Okay. Let's move on to the next part. Okay, suppose I take transpose, then what would happen? I'll get A, If I take again transpose to the transpose, I'll get A. And similarly, here I would like to enumerate, apart from other properties, I would like to emphasize upon AB transpose, that is B transpose into A transpose. Okay. There is a reversible property here. We'll get B transpose into A transpose. As we know, it won't be equal to A transpose into B transpose in most of the cases. So then we move on to the next. Yes, students, are you all good? So symmetric matrix we talk about. Symmetric matrix is a matrix in which we have what do we have in symmetric matrix? That A is, let us say, this matrix, then A transpose is this. What do we find? We find that A is equal to A transpose. Am I right? So whenever A is equal to A transpose, we get the matrix as a symmetric matrix. So when do we have this? When do we have this? Tell me. When Aij is equal to Aji. Am I right or wrong? So I'll go to the previous slide once again. I'll write the property here. When does it happens? What is the property which will make it happen? This is what? This H is A12 and this H is A21. So what do I have? Whenever in a matrix I have AJI equal to AJI, then it happens. Then it is a symmetric matrix. Okay. Then what about a skew symmetric matrix? A skew symmetric matrix, whenever we have A dash is equal to minus A. Am I right? A dash is equal to minus A. So here what do we realize? That the diagonal elements happens to be 0, 0, 0. It's a square matrix only. And we have here Aij is equal to minus Aji. Am I right? Aij is equal to minus Aij is equal to minus Aji. Okay. So for this purpose, when I is equal to j, that is for the diagonal elements, we have Aii is equal to minus Aii, or this would give me 2Aii is 0. That means the diagonal elements are 0. That's why we get this. Okay, students. So symmetric matrix we have done. Now tell me one thing. Suppose you are given, let's say 3 elements. Okay, let's think of a good question. Suppose you are given 3 elements. Apart from 0. So you are given 0 and you are given digit 1, you are given digit 2, you are given digit 3. These are 4 digits given to you. You can repetitively use these digits. Okay. Now you have to form a 3 by 3 symmetric matrix. Okay, or maybe not symmetric. Yeah, chalo, first of all we'll do symmetric. Symmetric matrix. Symmetric matrix you have to form 3 by 3. In how many different ways you can form a symmetric matrix? Tell me. 3 by 3 symmetric matrix you have to form. How many you can form? Nowadays there are a lot of questions which involve permutation combinations with the matrices or determinants. Tell me, students, think of it. So we have a 3 by 3 matrix. I can make use of 0, 1, 2 and 3 any number of times I wish. Ankita Yadav, you are giving me 18 as your answer. Solar DX, you are giving me 18 as your answer. Okay. So Lucifer G, 4 power 5. Okay, 4 power 5, Lucifer G. So let's analyze this problem, students. Jatin Raj 18, Raj Verma 18. So by symmetric matrix we are making. So diagonal elements I can make use of any. Do you understand it or not? Jatin Raj 18, Raj Verma 18, Dilip Ratha 18. So diagonal elements I can make use of any element. Am I right or wrong? So there are 4 choices for the diagonal elements. There are 4 choices for the diagonal elements. Okay. Now this place I need to fill in. So what is the what number I can place it here? There can be 4. So whatever number I'll place here, let us say if I place 3, then I'll have to place 3 here. Am I right or wrong? Rekha Rustagi 18, Tanya 2 raised to power 9. Let's see. So this is the diagonal scenario. That would be 4 cube. Diagonal elements can be any. Then this place can be filled by any of the 4 ways. This place has to be taken the same at whatever we fill here. Or you may write 4, this place 4, this place 4. This has to be replica of these, reflection of these. So this is one way only, one way only, one way only. So I get 4 cube more. Am I right, students? Giridhar 4 raised to power 6. You are right, Giridhar. Akash Saji 2 raised to power 9. No, why it is 2 raised to power 9? It would be 2 raised to power 2 raised to power 6. So if we get an answer in terms of 2, it would be 2 raised to power 12. Am I right? 4 raised to power 9. Solar DX. Why it would be 9? It would be 6 now. 4 this, 4 this, 4 this, 4 cube this. So it would be this. Am I right, students? That would be 2 raised to power 12. Okay, students, enjoyed? Now how many oh sorry, we were doing this question, no? Yeah, here we were. And how many skew symmetric matrices you will form? Okay, skew symmetric matrices. The next challenge, same question, skew symmetric matrices you have to make. So how many skew symmetric matrices you will make? You can now think in a proper way, है ना? Easy, surely, but steadily. Dilip Ratha 8. Only 8 skew matrices you will be able to form. Are you sure of that? Okay. 4 raised to power 6. No, sorry, Lucifer G 4 raised to power 3. Think of it properly, beta. 4 raised to power 3, Lucifer. Giridhar Sunil 4 raised to power 3. Okay. Hello. For anyone else who is giving me an answer? Anyone else? Yes. Sanskruti 16. Srinidhi, you are giving me 4 raised to power 6 as your answer. Jatin Raj 16. Satvik Reddy 2 raised to power 6. Okay. So let's see. By here only 0, 0, 0 would come. है ना? So for the skew symmetric matrix, the diagonal elements we have a position of 1. I mean only one option is there. Asmita, you are giving me 4 raised to power 3. Okay, just hold on. What is this place can be filled in how many ways? 4 ways. Am I right? And this place has to be exact opposite of this. But they can interchange as well. I hope you understand. I mean, suppose you write here 3, then minus 3 has to come here. But if 3 is here, then minus 3 can be here. Am I right or wrong? Hello? So first of all, not 4, 3. I'll make use of 1, 2, 3. If 1, 2, 3 is used, then it can be done in, if only 1, 2, 3 is used. Okay? Then it can be done in 3 ways here. And here it would be done a negative of that. So it can be exchanged also. है ना? So I'll get 3 into 2, 6 ways to place A12 and A21. Am I right? 6 ways are there. Okay? Giridhar Sunil, only 2 you are saying. So similarly, this place can be filled in 3 ways. So 3 into 2, that into 3 because there are 3, है ना? 6, not into 3, sorry. 3 into 6 cube. Because this place can also go in the same way, this place can go also in the same way. Am I right? नहीं, we can take negative values. Akansha, I told you in a skew symmetric minus is taken. Negative and plus you can make use of. Any number of minus or plus. Okay. Minus and plus have to be used. Okay. So I made use of 1, 2, 3. Okay. Now, so this is the case when 0 is not used. 0 is not used at the non-diagonal position. Okay. But still we have not reached the answer. Listen to it. Now when 0 is also used. So I am using 0. So whenever 0 is used, suppose I make use of this and I put 0 here. Then I can put 0 here. And these two places, this one and this one and this one and this one, can struggle with 3 into 2 raised to power 2 ways. Okay. Now similarly I can place 0 here and 0 here and not here and here. Okay. So this would give me into 2. I'll explain you in a more loose way. Okay. Let me have some space. Just a moment, students. Let me have some space so that I can explain you in a better way. Okay. You have to understand that we have a 0 also. So whenever at a non-diagonal position I have 0, then only 0 has to appear at the other reflective end. Then in that case into 2 won't come in. Okay. So skew symmetric matrix we are doing. So let's see. We'll have to make cases. Case 1. Case 1 is when I'm not making use of 0. No 0 involved at non-diagonal position. Okay. Non-diagonal position. So what do we have? We have this case 0, 0, 0. This place can come in 3 ways. I mean 1, 2, 3 I can place here. If I place 2, I'll place minus 2 here. If I place 2 here, then I place minus 2 here. So how many cases do I get? I get 3 into 2, and there are 3 places for it. This one, and this one. So whole cube. These are the number of ways. Okay. So how many do we get? 6 cube. These are the case when 0 is not being used at these non-diagonal positions. Case 2. Case 2. Case 2, 0 is used at one position. Okay. 0 is used at one position. Okay. So here let us say this is 0, this is 0, this is 0. I place 0 here, so I'll have to place 0 here. Then this place can be made use in 3 ways out of 1, 2, 3. This place in 3 ways, and this reflection of this, so 1 and 1, and this can interchange. So I'll have 3 into 2 whole square. Am I right? So that is 6 square. Am I right? Case 3, sorry. Case 3 would be 0 is used at 2 positions. If 0 is used at 2 positions, then it would give me 3 into 2. That is 6 places. And case 4 would be when 0 is used at all the positions. When 2 positions, when I'm saying 2 position, 1 position, I'm referring to the non-diagonal positions. 0 is used at all positions. That is all the 3 positions I'm using u0. So that would be 1. Only one matrix would be made. So what is the total we are getting? We are getting 6 raised to power 0 plus 6 raised to power 1 plus 6 raised to power 2 plus 6 raised to power 3. Am I right, students? Hello. So what's this? 1 plus 6 plus 36 plus 216. Somebody has done the total for me. Jatin Raj, I think, yeah, that is 259. That would be the correct answer. Am I right, students? I hope I made you understand. So here when I say 2 position, 1 position, I am referring only to the non-diagonal positions. Non-diagonal positions. Okay. Okay, students, let us move forward. So what do we have after this? Properties of symmetric and skew symmetric matrices. So what are the properties? Let's say in this case we'll highlight that if A is a square matrix, then A dash A are symmetric matrices. Okay. Then all positive integral, this is for symmetric matrix. All positive integral parts of symmetric matrices are symmetric matrices. So that means A raised to power n would be symmetric, but if A is skew symmetric, then minus A, Ka, A dash, A raised to power n, and A raised to power minus n. No, A raised to power n would be a symmetric only is written. Sorry, B dash AB. Please note that B dash AB are also symmetric matrices. Okay, wherever n is belong to natural number, K is a real number, and B is a square matrix of order same as matrix A. Am I right? Yes. Okay. Rekha Rustagi, you are saying something. Only 4 square matrix. I didn't get you. Can you explain it a little bit more, Rekha? What you are saying? Then let us talk about if A is skew symmetric matrix, then what happens? Then if we take the even power of A, only for a square matrix. Yes, it's only for a square matrix. Yeah. is a symmetric matrix for n belonging to an symmetric and skew symmetric matrix exist for square matrices only, no? Yes. So it is a symmetric matrix. So even if A is a skew symmetric matrix, I get A raised to power 2n as symmetric matrix. And if it has an odd power, we get a skew symmetric matrix. Okay? Then Ka is also skew symmetric. B dash AB is also skew symmetric. Obviously, the multiplications should be defined. And if A and B are symmetric matrices, then if A and B are symmetric, we are taking the case of symmetric, A plus minus B, AB plus BA are symmetric matrices. AB minus BA is a skew symmetric matrix. And if AB is symmetric, when I write I double F, it means if and only if. AB is a symmetric matrix, so of course we are talking about square matrices. AB is equal to BA. Then only it is then AB is a symmetric matrix, or the other way around. Both of the things are correct. Okay. Buffering, I don't think so. My side, the transmission is perfect. Okay. Please refresh your page. So we go to the next one. What's that? If A and B are skew matrices, so if in case we have AB, you please learn these, Buffering, my side it's okay, beta. If A and B are skew symmetric matrices, then A plus minus B, AB minus BA are skew symmetric matrices. AB plus BA is a symmetric matrix. Okay? And here comes an important thing. If A is a skew symmetric matrix and C is a column matrix, C is a column matrix, okay? Then C dash AC is a zero matrix. Please learn this. Okay? Keep this in mind. Yes, okay? Can you explain second point of 5? 5? Where is 5? Okay, after 4th they have given you 6th. Okay, just a slight mistake. Can you tell me, Abhimanyu, which you are referring to? The previous slide you mean? 5th. Okay, second part. AB minus BA is a skew symmetric matrix. That's what you want me to explain? Second point of 5th. Okay, let's take it. So we have AB minus BA is a skew symmetric matrix. So let's see, A and B are symmetric matrices. So AB minus BA, transpose, let us say what we see it as. So when we take transpose, we will get AB transpose minus BA transpose. Will I not get this? So this would be what? This would be, this would be B transpose A transpose minus A transpose B transpose. Am I right? So this I can write it as minus common, and I can write it as A transpose B transpose minus B transpose A transpose. Am I right? Okay. So this can be written as minus AB transpose. This can be written as BA transpose, BA transpose. Am I right? And this can be written as BA transpose, A transpose, B transpose. This can be written as AB transpose, So this would eventually become minus of BA, minus of BA minus AB transpose. Okay, there's a slight mistake here. I think AB minus BA is a skew symmetric matrix. This is what you want me to explain. I take a transpose here, so I get AB transpose minus BA transpose. Okay, okay. Thank you, Sai. Theory you have already done. I'll go for the practice session, beta. I'll go for the practice session. No worries. So AB transpose, I'll get this as B transpose A transpose minus A transpose B transpose. Yeah, so how it would be symmetric, skew symmetric. That's a little challenge. So this is what we get. B transpose A transpose minus A transpose B transpose. But if we put it back, then we get the same thing. I know. You're right only. Yes, Akshay Shekhar, a very good morning. This won't fetch me a skew symmetric matrix. A skew symmetric would have been if I get minus BA, है ना? Minus transpose, this is what I get AB minus BA. This is when this I'll get, है ना? Tell me, अच्छा, when B transpose, now this I should get. Now tell me, what is B transpose? Here, this is step I work out. B transpose, B is what? A symmetric matrix. So B transpose I can write B, है ना? A transpose I can write A because A and B are symmetric matrices. And minus A dash I can write it as A and B dash I can write it as B. So is this correct, student? You understand? So it's right only. The second is right. AB minus BA is a skew symmetric matrix. I hope you understood. Who was asking this problem? You understood it? Hannah? Yes. So we come to the next question. Okay. Next, not question. We'll go to the elementary row transformations. So row transformations, whenever we talk about, these properties are important, no doubt about that. But in any case, in row transformations, proofs are required. So we'll not go into depth of this theory, row transformation. But there is a specific and exact method for which any 3x3 matrix you can reduce, you can get by elementary row transformation, you can convert it into a unit matrix. Okay, determinant of a matrix. We come to determinants, students. Okay, so determinant of a matrix, you understand, for a square matrix we can calculate the determinant value. This is all very common to you, Then 3x3 determinant we calculate by this method. That's also very simple. Now here I can ask you one simple problem, and that has been asked in a typo of has been asked in IIT. Okay, we are making a, yes students, please focus. We are making a 3x3 determinant, okay, 3x3 matrix determinant, and we'll make use of only 0 and 1, okay, 0 and 1 we'll make use of. These are the two elements which we'll make use of. Then tell me how many, now if how many determinants you will form. First of all, tell me this. How many determinants you will be able to form? Different determinants. Okay. Rekha Rustogi 512. You mean to say 2 raised to power 9? That's what you want to say, Hannah? Tarun, 4 determinants only you are speaking of. You'll be able to make only 4 determinants. Acha, by the way, Rekha, if I get a determinant like 0, 0, 0, 1, 1, 1, 1, 1, 1, Hannah? This is one determinant, है ना? Abhimanyu 2 raised to power 9, Meenakshi Sundaram 2 raised to power 9. That is the number of matrices which you can make. Am I right or wrong? That's right only, because first place can be done in 2 ways, second place can be done in 2 ways, third place can be done in 2 ways, fourth place can be done in 2 ways, and so on and so forth, है ना? So that gives me 2 raised to power 9. 2 raised to power 9. Okay, but now the question begins. The actual question is now only. Okay, the question is how many determinants you can get, how many determinants value non-negative you can get. non-negative you can get. Okay. Non-negative determinants you have to form. Okay. Now you tell me. It's difficult. Okay. Okay. I reduce your problem. I'll non-negative determinant. I'll take a 4 by 4 determinant. Okay. 1, 2, 3, 4. 2 by 2 determinant only. 2 by 2 matrix determinant. Now you tell me how many non-negative determinants you can form instead of this. Okay. Yes. So we are making a 2 by 2 matrix determinant. How many non-negative value determinants you can form? Okay. Go ahead. Non-negative determinant value. Value of the determinant should be a non-negative number. How many you can form? Okay. Yes, students, I'm waiting for the answers. Tarun 3, Rekha Rustagi 8, Abhimanyu 3. Yes, you're right. Non-negative determinants, it would be Jatin Raj 4. Okay. So let's see. Non-negative, in non-negative we get the answer Sol RDX 3, Lucifer 8. We get, I mean non-negative when I'm speaking of, non-negative means I can get 1 or I can get 0. है ना? Non-negative means 0 also I'll include. Okay. So the first one, 1 is here, 1 is here, 0 is here, 0 is here. है ना? So what's the result of this determinant? 1. Am I right or wrong? Then I can get 1, 1, 1, 0. This will also be 1. Then I'll get 1 minus 1, 1 minus. Non-negative. Non-negative means I get the result as 1 or 0 or anything else. है ना? Then I get 1, 1, 0, 1. Okay. Hello. This would be 1. But will you consider these two determinants separate or same? I'll consider them separate. Okay. So 3 I get. Then non-negative I'll get 1, 1, 1, 1. This would be 0. So non-negative 0 is included. है ना? Then I get 0, 0, 0, 0. This I get 0. Am I right? In fact, the better way is to find negative determinant value. This only I'll find. So instead of this, I'll only find how many total I am getting. Total number of determinants are 16. Am I right or wrong? Total number of determinants I am getting 16. So I'll find the negative determinant value and that I'll subtract from the total one. Total from that is 16. Okay. So I'll find the determinants which give me a negative value. Am I right? So negative value, how will I get? This would be 1, 0 and here it would be 1, 1. So that's minus 1. Then here it would be 1, 0, 1, 1. That's minus 1. And then the last one 0, 0, 1, 1. That's minus 1. So only 3 I am getting. Am I right? Negative I am getting 3. So from the total of 16 I'll subtract 3. So I'll get 13. So non-negative determinants are 13. Am I right, students? Non-negative determinants. I hope this is okay. Yes, Abhimanyu Gupta, 13 is the right answer. Okay, superb. Thanks. Thanks, Tarun. So, what do we get? Singular and non-singular matrix. Okay. Now, singular and non-singular matrix. What are singular matrix? Singular matrix are matrices whose determinant value is 0. That's what they have given. A square matrix. First of all, obviously the determinant value has to be calculated, so it has to be a square matrix. Singular matrix if its determinant is 0. Otherwise, it is called a non-singular matrix. Then, yes, thank you, Abhimanyu. So, we go to the next slide. properties of a determinant of a matrix. Okay, here what do I have? I have AB are square matrices of same order, determinant A, determinant AB. Determinant AB is equal to determinant A into determinant B, है ना? They have not written it here. It is determinant A into determinant B. Okay? I mean, this I can write it by pen as well. I'll write it just afterwards. If A is an orthogonal matrix, you know what our orthogonal matrix is? And determinant A would be plus minus 1. A is a skew symmetric matrix of order. A is a skew symmetric matrix of order odd order, है ना? Then determinant A is 0. Okay. Yes. Interesting topic. Yes, that's very good, Achit Shikhar, because you would then be required. I mean, complex. Computer engineering, everything would go with matrices and determinants, because computer generally understands everything in the matrix language. So matrix algebra becomes very important. Okay. If A is a symmetric matrix of even order, you please read. If A is a symmetric matrix of even order, then determinant A is a perfect square. Wow, what an information. Meenakshi Sundaram, orthogonal matrix. Can somebody explain me what's an orthogonal matrix? Hello? Can somebody tell me what is an orthogonal matrix? A into A transpose is identity matrix. That is an orthogonal matrix. Okay? Yes. Then Ka. Now, this is important. Ka determinant is k raised to power n determinant A. Actually, n is the number of elements in set A, in the matrix A. N is the order of A. You can say it as order of A. Okay, since k is a scalar multiplication and it will get multiplied to each element of the matrix, so it will raise overall determinant value by n. Now, when n, I am saying it as an order of A. Actually, order in complete sense. I mean, 3 into 3, it would make it 9. I hope you understand. Don't confuse it with. Because n is order, third order, I won't say. It won't be 3, k cube. No. If A is a determinant of 3 by 3 order, then k raised to power 9 would come here. Because each element of matrix, it will raise overall determinant value to k raised to 1. Acha, sorry, I got it wrong. Yes, you're right, Giridhar. Transpose is the inverse of an orthogonal matrix. That's what I said. A into A transpose is identity matrix. So, just a moment, I'll explain it to you here. Suppose you got a 3 by 3 matrix. Now, 3 by 3 matrix, you multiply it by 5A. So, you'll get 5 cube A, determinant A. Why? Because when I write 5A, every element of A matrix will get multiplied. A11, A12, I mean, this would be 5 into A12, this would be 5 into A13, and so on. So the first column I'll take, first row I'll take 5 common, second row I'll take 5 common, third row I'll take 5 common, so I'll get 5 cube. So n is the order of A, that is the third order, so 3 would come out here. Okay, I hope this is understood. No confusions? So next we shall go with some value, minor of an element. So minor is already understandable, you know, but little bit of revision is required. So if we want M11, minor of 11, that is A11, we'll see whatever row it is coming in, we'll erase it. We'll erase the column in which it is. So whatever is left, that determinant I'll form. Okay. And here this is the value of the minor of an element. Okay. I hope this is okay. And then we have, okay, tell me one thing here for a minor of an element, that we don't use the value, minus plus is not used before it. When that would use, we'll make it as a cofactor. Srinidhi, involuntary. It's not involuntary. It's involuntary. A square is identity matrix. Right only, Srinidhi. So that is involuntary. Cofactor of a matrix of determinant is the minor of the matrix. That is not all required here for JEE mains. Okay. But the only difference is sign. I plus j is even, then cofactor minor I plus j is odd. So we have this relation. I hope everybody is comfortable with cofactor and minus. Not a very I mean, that's all, everybody understands this. Okay, we come to adjoint of a matrix. Here the properties of adjoint of a matrix will become very important. Okay, how do we get the adjoint of a matrix? Tell me. If we replace each element of a matrix, if we replace each element of the matrix by its cofactor, then we take the transpose of that given matrix, that is transpose of the cofactor matrix. Tarun, you are becoming so hungry. Just give me 5 minutes, 10 minutes. 10 minutes, the session will end. Okay? And 10 minutes only, I promise, Tarun. Okay? We just need to find the cofactor of every element, take the transpose of the cofactor matrix and just change. Okay? Then you get the adjoint of a matrix. Okay, students? So what is an adjoint of a matrix? It is the transpose of the cofactor matrix. Okay? So that's how it is formed. Okay? Involuntary matrix. Beta, Meenakshi, involuntary matrix is whenever we get A square as an identity matrix, then A is known as an involuntary matrix. Then we also have idempotent and all those matrices. That is not required here, beta. That is not required. Okay? Properties of adjoint of a matrix. Now this becomes important. Please focus on this. So what do we have? Non-singular matrix. What are non-singular matrix? Just make me remind. That is determinant A is not equal to 0. Adjoint of A determinant. Now please see, the question will come from this. Determinant of adjoint A mod A raised to power n minus 1. Okay? Then AB are a square matrix. It follows a reversible property. Adjoint of AB is, no Tarun, I'll finish within 10 minutes, no problem. Adjoint of AB is adjoint of B into adjoint of A, okay? Then if A is a square matrix, then AB adjoint of A transpose is adjoint A transpose. Then look at this. This is very important. Adjoint of A. This is determinant A raised to power n minus 2A. Okay? Please learn this right now. Adjoint of adjoint A, we get determinant A raised to power n minus 2 into A, where n is the order of the matrix. Okay? So similarly, A is a square matrix and K is a scalar. Then adjoint of K is K raised to power n minus 1 into adjoint of A. Now this property you might not have seen. Adjoint of K into A. Example problem, Ashit Shikhar. Adjoint, I would rather not like to give you any example. This would be just obvious, just putting these properties, solving of these properties. There won't be any innovative questions based on this. Wherever innovative questions would come, I'll give it to you. Okay? Here making use of telling order is 3 and adjoint of A is this, and then asking you, that would be easy only. Then inverse of a matrix. Inverse of a matrix is when adjoint of A is divided by the determinant. That's how we get the inverse of a matrix. Okay? And in any case, example problems we are going to practice matrices and determinants tomorrow. The inverse of a matrix is, that's how we get. Okay? I hope everybody is aware of this. Okay. Then let us talk about properties of an inverse matrix. The properties of an inverse matrix, every matrix, non-singular only, has a unique inverse. Every matrix is having a unique inverse. That's a uniques, okay? Gauss-Jordan method. Oh, where did you get that? Every matrix has a unique inverse. A and B are invertible matrices of order n, then AB will also be invertible. Okay, So what does it say is if AB are invertible matrices what are in, then AB will also be invertible. Please can you focus on this, Tarun, instead of going outside the scope of our studies. AB inverse is B inverse A inverse, that's a reversible law. If A is an invertible matrix, then A dash will also be invertible. If A be an invertible, K is a natural number, then A raised to power K minus 1 is A minus 1 K raised to power K. Okay? Let A be an invertible matrix, then if I take A inverse and again inverse, then I'll get A. And here it becomes important, determinant of A inverse is 1 by determinant A. Okay? Okay, students? All fine? Huh? Okay. Then properties of determinant. First property, changing rows and columns, there's no problem. The value is same. Hai na? Then property 2, if any of the two adjacent rows or columns are interchanged, we get minus in front of it. Hai na? I mean, those are few properties which you have already learnt in your 12th standard. But here we are just going in for a quick revision. Abhimanyu Gupta, what's that? If AB is 0, second point, what are you referring to? Please explain. Second point, which one? That, no, if AB is equal to 0, which point you are referring? Please refer it. Property 3, if there is twice interchange of rows or columns, then the sign doesn't change. So delta n is the determinant obtained by n successive operations. Then delta n is if such operations, if n is odd, I mean this all is, you know, if n is odd we get minus delta, if n is even we get delta. We go to the fourth. If any, we are coming to that, Tarun, homogeneous solution and all that. If any two rows or columns of a determinant are identical, all corresponding elements are same, then the value of the determinant is 0. Okay. Then if each element of a row or a column of a determinant is multiplied to constant, then the determinant is multiplied by k. This all is okay. Then this is if every element of sum of, I mean I can split into two determinants. That's obvious, that's quite obvious from this thing. Then property 6 I've got. Then property 7. If to each element of a row or a column of a determinant, the equimultiples of corresponding elements of other rows or columns are added, then the value of determinant remains the same. Okay. So R is R1 plus KRJ, Ci is Ci plus KCJ. And at a point, one row or column has to be same. A is invertible and B is invertible. Then AB is invertible. Yeah, that's right. AB is invertible. Okay. That would come, okay, Abhimanyu. You were talking about that. AB would not be equal to a null matrix, beta. If A is invertible, you please focus. What do I have? I have, I'm referring to Abhimanyu Gupta. He says if A is invertible and B is invertible. If A is invertible and B is invertible, what is the determinant value of AB? Tell me. Determinant A into determinant B. Am I right or wrong? And this is not 0. And this is not 0. Then this is also not 0, na? Okay. So if, I hope you understand. So then I can get the invertible of AB also. AB is invertible. Am I right? Okay. Now, if each element of the side, one side of both sides of the principal diagonal of a determinant 0, then the value of the determinant is the product of the diagonal elements. Please look, if we want to find out the value of this determinant, then I just need to take the product of the determinant elements. Okay. Then I hope I answered you, Abhimanyu. Then we come to determinant. D becomes 0. Okay, this is the factor property. Please focus, everyone. If a determinant D becomes 0 for x equal to alpha, okay? Yani x minus alpha is a factor of delta. In other words, if two rows or two columns becomes identical for x equal to alpha, then x minus alpha is a factor of delta. Okay? So what we see, we have considered an example. So we have x square, x cube, and we have these values. When x equal to 4, if I put, then the first row and the second row becomes identical. Row 1 and row 2 becomes identical. Then at x equal to 0, delta becomes 0. So all elements of R1 become 0. Okay. So that means x minus 0 and x minus 4 are factors of delta. So that means if I want to reduce the determinant, or if I, what do you call that? If you want to write it without expanding, if you want to write it, then it would come x minus 4 and some other delta dash would come, delta 1, let us say. The x and x minus 4 would become the factor of the determinant, and the delta 1 you will obtain when you will take x and x minus 4 as common out of this. I hope I made you understand. Then we have system of linear equations. Okay, system of linear equations. We quickly go through. Consistent equations. What are consistent equations? Consistent equations are those which have at least one solution. This is important. That means even if we have infinite solutions, they are consistent equations. Okay, has at least one solution. So a1 by b1 is not equal to a2 by b2. Given lines are non-parallel, hence lines will have one point of intersection. Okay, but if they are coincident, then also it would be consistent equations. Okay, I hope you understand. Infinite solutions also means consistent. So here we come to inconsistent equation. Inconsistent equation when a by a2, when the lines are parallel, a1 by a2 is equal to b1 by b2, not equal to c1 by c2. So this is the condition for inconsistency. In this case, there would be no solution. Then dependent equations. These are dependent equations. They have infinite solution. Why? Because the lines are coincident. Okay. Cramer's law. Okay. If determinant way of solving the equation, that is if the determinant is given, then I can find out the values of x, y, z. Unique solution I'll get when the system of equations, if delta is not equal to 0, we have a unique finite solution, and the solution is given by x equal to delta 1 by delta, delta 2 by delta, delta 3 by delta. You know what is delta 1? Delta 1 is the determinant which is obtained by replacing the first column with the constant d1, d2, d3. I hope everybody remembers this. Mayank, good morning. You are late. Yeah, no problem. Join us. And if delta is 0, and if any of delta 1, delta 2, delta 3 is 0, then in that case the system of equation is inconsistent, and hence no solution exists. Okay, this is not in the syllabus, beta. Gauss-Jordan method. Yes, Tarun? And if all delta 1, delta 2, delta 3 are 0, the system of equations are consistent and dependent, and they have infinite number of solutions. Okay, infinite number of solutions. Okay, yes, students. Then we have what? Matrix method, system of linear equations using matrix method. This is the last topic which we are doing. So what's that? Tell me. If the system of equations are given as a1, I hope everybody knows this, a1x b1y plus c1z is equal to d1, and we have a2x plus b2y plus c2z is equal to d2, and a3x plus b3y plus c3z is equal to d3. Matrix method, everybody remembers. I'll just enumerate the the solutions to it. So matrix A would be a1, a2, a3, b1, b2, b3, C1 C2 C3 है ना, and X would be the column matrix X Y Z. Yes, you're right, Tarun. And B would be the column matrix D1 D2 D3 है ना. Okay, now I'll take up an innovative question in this. I hope everybody is comfortable with this. I can write this system of equation as Ax is equal to B. So if determinant of A is not equal to 0, then the solution is X is equal to A inverse B. है ना? This gives a system of unique solution when determinant of A is not equal to 0. Okay, that's how we get. Then second point is if adjoint of A into B, adjoint of A into B is a null matrix. Okay, then we have infinite solutions. And if it is not equal to 0, then we, bus last topic Jatin, last topic. And if this is not equal to 0, then we have inconsistent equations. No solution. Okay. So now I give you a question. Let's say there is an equation like lambda x plus 2y minus z is equal to 1. Then I have 2x plus y plus z is equal to 2. And I have 3x minus y plus 2 lambda z is equal to 3. Okay? Acha, okay Jatin, I'm just finishing it off. So, in what are the values of lambda? Okay, what is the value of lambda so that the equation is consistent and give you a unique solution? I mean, there are unique solution. Can you do it? Sai, tomorrow I'll be taking questions only. Okay. Actually, on demand of students, we took theory as well, Sai. So from next tomorrow, I'll be taking questions only on matrices and determinants. Okay. There's nothing bad. Revision of 1 hour. That's not a bad. Consistent and unique solution. What is lambda? Okay. Come on. Give me an answer. So what do we have here? We have lambda 2 minus 1, 2, 1, 1, 3 minus 1, 2 lambda. है ना? This should be equal to 0. Am I right? Not equal to 0, I mean. Not equal to 0. Okay, Rekha Rustagi 4. Unique solution you will get when this is not equal to 0. So how you can get a single answer, beta? So you get lambda. I mean, I'm solving it. This goes this. This is 2 lambda plus 1 minus 2. This is gone. This is gone. 4 lambda minus 3. And then you have minus 1. This is gone. This is gone. 2 minus 1 is minus 2 minus 3. That should not be equal to 0. Am I right? So what do I get? 2 lambda square. What do I get? Lambda and minus 8 lambda. That is minus 7 lambda. And what else? 6. And this is minus 2 minus 3 is minus 5 and plus 1. That is plus 6. That is 12. Okay? You will get something like that. You're right only, Jatin. Not equal to 4 and minus 6. Okay, let's see. So, lambda and minus 8 lambda. So, I get 2 lambda square minus 7 lambda plus 12 is equal to 0. Okay. 12 2 ja 24, 8 3 ja 24, 6 4 ja 24. I'm not getting a total of 7. So, I'll get lambda. I take the next slide. Not equal to 0, I'm writing. Not equal to 0. है ना? So all R, lambda would be all R except the values which I'll get here. So what was the equation? Can I get it? 2 lambda square minus 7 lambda plus 12 is equal to 0. Can somebody tell me what is the determinant of this equation? It is 7 7 49 minus 4 to the 8. 8 into 12 is 96 if I'm not wrong. 8 to the 16 1. Yeah, 96. It's negative. So this implies 2 lambda square minus 7 lambda plus 12 is always greater than 0 for all values of lambda belonging to real numbers. Okay? Am I right? So that means for all values of lambda, all lambda belonging to real number is the right answer. Am I right? Hello students. It will be plus 11. I did some mistake beta. Just hold on. Acha, plus 5. You're right only. Sorry, I'll get plus 5 here. I did a slight mistake. It is 5. You're right only. It would be 11. है ना? Yeah, right. So there would be a different answer in this case. Just a moment. So what lambda we are getting? We are getting lambda as Jack Sparrow. Good morning. Okay. So we have 11 here, not equal to 0. 11 here. Let's see what the answer entails. So it is simple only after this. So we get 11 to the 22. 22 into 8 is what? 22 into 8, 22 into 4 is 4 to the 8, 4 to the 8. Then also it is less than 0. है ना? 49. 7 square is 49, na? B square. 7 is square. B square minus 4AC. That's what determinant is now. Minus 7 square is 49. 7 square is 49. 2 lambda square. Why 2 lambda square? Why there is a problem by determinant is what? B square minus 4AC. Am I right? So B is what? Minus 7 whole square minus 4 into 2 into C. Am I right? So what's that? 49 minus 88. Am I right or wrong? Tell me. Just give me a node. Yes or no? So is this not less than 0? Hello? Hana? So we get 2 lambda square minus 7 lambda plus 11 greater than 0 for all values of lambda belonging to real number. Okay? Yes. So all values of lambda is the answer. Okay? So for no values of lambda, the question was, what was the question? Question was that for what values of lambda it is consistent and unique. So what is the answer? All real numbers. Okay? So yes students, we wind up the session here. I hope you understand. Hana? So is this okay to all of you? Tomorrow we are going to do problems on matrices and determinants. So you get ready with your pen and paper tomorrow and we'll solve. Okay, tomorrow we are going to make one simple way that everybody will take note of how many questions he or she has done right. And for every right question you will get plus 4 marks, and for every wrong answer you get minus 1. Okay, you get minus 1. Yeah, MCQs on matrices and determinants. That's what. And in the final tally we'll calculate how many what students will get marks, how many marks each student will get. Okay, so there will be a competition tomorrow. Okay students, bye bye. Yes.